In this day and age, computational tools for predicting and qualifying the performance of engineering systems are becoming increasingly central to analysis workflows. Unfortunately, it's often inadequate or even impossible to assume real-world knowledge of inputs to even the simplest of our computational models, and it's this uncertainty that motivates my research. My name is Thomas Roberts, and I'm a graduate research assistant in the Advanced Engineering Analysis Group E13. In my work, and under the guidance of my mentors, Scott Allett and Adam Wachter, I focus on studying the effects of model form uncertainty in computational models throughout the entire engineering lifecycle of vibration absorption systems involving closed-cell foams. To illustrate this, I'm going to spend a few minutes today talking about different forms of uncertainty in engineering systems, how we are studying and quantifying the effects of these uncertainties, and how we as engineers can support a full lifecycle analysis from a computational perspective. The overarching question that this presentation aims to answer is how do material parameters, preloading, and environmental conditions affect the dynamic response of a suspended mass and closed-cell foam system. I want to break this question down into four main areas of study, the first of which is parametric modeling. Here we use parameter sampling strategies to help us inform our engineering quantification of margins and uncertainties. We then want to use these techniques to help us understand how uncertainties in the manufacturing process, assembly conditions, and environmental inputs will change the dynamics of the system. In short, this work aims to answer how uncertainties in the manufacturing process and assembly conditions can change the mechanical response of the material. And then finally, we want to know how that, coupled with uncertain environmental inputs, can change the frequency response of our system. At this point, I've probably used the words hyperelastic and closed-cell foam a couple of times, and I want to formally define this here. Hyperelastic foam models can describe a specialized class of materials that tend to respond elastically when subject to large strains. These types of models can describe large volumetric changes and nonlinear stress-strain behaviors, the latter of the two which will be of primary interest to us as we start to think about the engineering challenge that is using these materials. With such a large parameter space of material properties and environmental conditions, closed-cell foam can be a very versatile tool for absorbing shock and vibration. Unfortunately, the mechanical responses of these types of materials can be very dependent on both intrinsic and extrinsic conditions, so uncertainties in the manufacturing process, assembly characteristics, and environmental excitations can make designing systems with these types of materials rather challenging. The first class of model form uncertainty I want to discuss in this presentation is uncertainty due to the manufacturing process. To look into this, we did an initial parametric study of our hyperelastic foam model where we varied 3 of 9 possible material model parameters to create a parameterized suite of finite element models. The direct simulation output of those finite element models is shown in the figure on the left, where we have a suite of 76 reaction force versus nodal displacement curves that represent the possible variability in mechanical response due to uncertainties in the manufacturing process. Furthermore, we wanted to see how sensitive the material model was to slight changes in its parameters. The figure on the right shows a material parameter sensitivity index, where a dark purple color indicates that a material parameter has a high effect on the output of the model, and a light yellow color indicates that the material parameter doesn't do much to affect the output of the model. What we can see here is that the initial porosity of the model, or this variable phi, shown in this dark purple color in the very top, has a very significant effect on the stiffness of the model over the entire operating strain regime of the material. So what we can gain from this is then knowing when we manufacture these foams, we absolutely need to know our value of initial porosity. Otherwise, we're going to induce some unnecessary uncertainties into our prediction. The second type of model form uncertainty that we're interested in is that due to the variabilities in assembly conditions. Closed-cell foams are specifically designed to be pre-compressed along a wide band of material strain regimes to allow us to design for specific dynamic characteristics for a particular system. To describe this, I want to go through a simple thought experiment where we have a mass suspended by 2 pieces of closed-cell foam, here represented as 2 springs. After some preloading or precompression is applied to the system, each spring is going to take on an equilibrium operating strain value, and that's shown here as the black dot on this reaction force versus displacement curve, meant to represent the general mechanical response of a piece of closed-cell foam. Naturally, in the harmonic motion of this system, the mass is going to move back and forth at a distance that we can call x and then ultimately each piece of foam is going to take on a different operating strain value that's going to change with time. And when we look at these red dotted tangent lines here on the curve, these represent the stiffness of the material. So as the mass oscillates back and forth, each piece of foam is going to take on a different value of stiffness as a function of time. And this is exactly the definition of a nonlinear stiffness, wherein the material stiffness is dependent on either displacement, time, or both. And knowing that our material has these characteristics, we can come to the conclusion that variations in the foam preloading during assembly can cause uncertainties in the stiffness of the system and thus will lead to some significant variations in the dynamic response. Our final consideration of model form uncertainty comes from unknowns in the environmental excitations around the system. Environmental unknowns can accentuate the system's nonlinear behavior, especially when we talk about things like large amplitude oscillations, where large deflections can lead to drastic changes in material stiffness, and strain rate sensitivity, which is a property of the material itself, wherein the faster the deflections are, the softer the material will respond. To illustrate how some of these uncertainties can affect the overall mechanical response of the material, I want to look at 3 specific cases. In each case, we're going to examine a force displacement curve shown on the left and a stiffness versus time profile shown on the right. In each plot, there's a red dot which represents the operating strain value of a piece of foam, and the 2 red dots in these plots are synced with time across all the animations. The first case I want to consider is when we oscillate in a nonlinear strain regime but with small displacements. And in this animation, I want to set aside the speed at which we're oscillating and pay most attention to the amplitude and the shape of the stiffness versus time profile. So we can see as we oscillate in this nonlinear material strain regime, we get some pretty significant changes in material stiffness over time, but this is just with small displacements, and this is far from the worst case scenario that we could possibly see. Now I want to look at when we oscillate in that same nonlinear strain regime, but with some larger displacements. Here we can see we get significantly larger changes in stiffness over time, and the discontinuities in the stiffness profile become much sharper, and this is going to have some rather adverse effects on our ability to make predictions about the dynamics of our system. To drive these points home, I want to consider one last drastic case where we oscillate in a highly displacement sensitive material strain regime. So we can see as our red dot oscillates over this sharp bend in the force displacement curve, we get some very drastic jumps in the stiffness over time, and this is going to make it almost impossible for us to design dynamic characteristics that we are interested in. So this should at least be enough motivation for us to see that we need to actually know something about the uncertainties in our systems, otherwise we're going to have these type of effects and not be able to design our systems effectively. Now that we've talked about all the types of model form uncertainty that we're interested in analyzing, I want to gloss over the computational tools that allow us to do just that. The first tool that we use is a full system finite element model that consists of 2 pieces of foam and a suspended mass in between the pieces of foam. This is an implicitly preloaded and explicitly excited system that's meant to replicate the real-world environments that could possibly be imposed on this system. The second computational tool that we use is a reduced order single degree of freedom mass spring damper model. This is a time-integrated ordinary differential equation that has nonlinear stiffnesses informed by the same parameterized material model and forcing conditions as the full system. And this second computational tool was meant to be an efficient way of giving us some sanity checks on whether or not our full system computationally expensive models are giving us reasonable results. At this point, you might be wondering how it's even possible to support this type of computational framework, but it's actually a rather simple process to explain. Any engineering baseline computational model, or template model you could call it, will have approximately the same 6 steps from start to finish. The first 3, which are geometry definition, meshing, and solver preparation, are generally going to remain consistent for any one template model. But it's once we get to the solve step where we can actually introduce our parameterization strategies. Here, we can take our 3 main sources of uncertainty, which were material parameters, preload parameters, and dynamic load parameters, and we can independently sample them from our nominal baseline model. Once we've done that, we can simulate all of these models simultaneously and then analyze them as a collective. And by doing this, we can create an agile and informative framework that allows us to properly assess how uncertainties throughout the entire engineering lifecycle of our system will affect our overall response, regardless of what the response of interest is. To conclude the presentation, I want to show some comparisons between a nominal model and some models where we considered the effects of each of these three types of model form uncertainty independently. Here, a nominal model has material parameters calibrated for a single material configuration, and then the model is preloaded and excited to moderate operating conditions. First, let's consider manufacturing process uncertainty, and to study this, we varied 3 of the 9 possible material model parameters, and the figure on the left shows the variability and frequency response that can result from that type of study. This figure shows us that just by varying these 3 material model parameters, we can get errors of upwards of 71% in this parameter space, and we see some pretty drastic shifts in the fundamental frequency of the system. We see even more uncertainty in the fundamental frequency of the system when we consider things like preloading uncertainty. Here, we varied the preload in the model from 0 to 48% strain, which represents the holistic operating strain regime of the material model, and we see even bigger shifts in fundamental frequency, sometimes upwards of 185% in this particular parameter space. And finally, we start to see some really interesting things occur when we consider uncertainties in the environmental conditions. In these models, a shock excitation was applied in the form of an instantaneous initial velocity constraint to the suspended mass, and the figure on the left is showing us that, yeah, even though we varied this initial shock velocity, we get errors of about 16% in this first fundamental frequency. However, some interesting things start to pop up as the intensity of this shock excitation starts to increase. Once we get to these higher levels of excitation, we can see that more peaks start to appear in the system's frequency response, and this tells us that the system is starting to become nonlinear in its vibration, and now we don't just have one natural frequency to design around, we have multiple that pop up at higher energy and higher frequency ranges. So the combination of all 3 of these types of model form uncertainties can have significant effects on the response of our model, and we need to consider this as we start to design our engineering systems, especially from a science-based and computationally based perspective. On that note, I'd like to thank you for your attention today, and I'd also like to thank the Lano Student Programs Office for organizing the very first ever virtual student symposium. I'd also like to thank my mentors and their supporting organizations, Scott Ouellette from E13 and Adam Wachter from the National Security Education Center. If you have any questions following this presentation, please feel free to reach out to me via email. I'm in the Lano phone book, or you can simply contact me at tproberts@lano.gov.